Yeah, so I'd like to introduce Ruchi and Johannes, and they talk about vectorizing consumer electronic goods.
Thank you. Good to be a technician finally. Yeah, we will talk today about how we deal with consumer electronic stuff. We started to implement a vector search by the beginning of the year. So we are in the mid of our journey, but we are more or less production ready, I would guess. So yeah, and today we will tell the story about the last month, how we made progress. I'm Johannes. I know many of you. Maybe it's the same vice versa. I have some kind of on-off relationship with MediaMarkt. So I started as an internal there, then I became a freelancer. Now I'm an external there. Yeah, good to be here again and to talk about consumer electronics.
Thank you. Hi, I'm Ruchi and I work as a senior data scientist at MediaMarkt Saturn. MediaMarkt is Europe's leading consumer electronics retailer. So we have stores both online and offline with over 1,000+ stores offline, but we have a larger share coming also from online stores. So today we're going to talk about vectorizing consumer electronics specifically. So vector search has been a buzz for over the past few years, but a quick question, has it taken over lexical search? No, not yet. What about, will it take it over the next years? Well, that's controversial. I'm not going to talk about it right now. But we know that hybrid search is a thing that is going on really well. And that's where we also kicked in and we thought, okay, we're going to use vector search as a fallback mechanism. So the first use case that we thought of was zero results. I think we're all aware of zero results pretty much everywhere. Before we started working on it, the first question was, why do we have zero results? What are the reasons or the core reasons that we have zero results? So we started analyzing our queries, zero result queries, started manually labeling them, and over the period of time, we created an algorithm that could classify these queries. So we created a bunch of clusters, recognizing why we have zero results. The first one, pretty simple, misspellings, though we have spelling correction. And also the fact that our Solr is quite strict with the matching. We do still have issues with misspellings, word breaks, compounding and decompounding of the queries. You can see some examples. Also special characters like Apple symbols instead of Apple as a text. So these doesn't work and we get spelling issues with zero result. Almost 11% of our zero result queries had spelling issues. The next one, very interesting with e-commerce, is series. So a lot of product queries are based on the series model. SJ25556 could be a washing machine model. Similarly, there are very specific queries with brand plus series model. And we have a lot of issues. Almost 32% of the queries from zero result are series model. And now there could be multiple reasons. It could be a misspelling in the series model itself, or maybe we sell it in a different way. So we have John Wick. We do sell John Wick DVDs, but not as John Wick 1 to 4, which is a series in combination. And then it could also be possible that we don't sell those products as is. So we do sell Apple products, but maybe not Apple Pencil cap. The next one was because of the semantic issues. So these are more general queries where user add more general terms like maybe a big washing machine, small, a home office, or let's say wireless, computer, Bluetooth. So these kind of generalized terms that are not part of the product description creates a lot of zero result queries, and it's mostly semantic. The other one is also kind of convention on how we state these products. So synonyms, one thing could be called in another way. And that's why we have zero results for that. Another one, language. So we are all across Europe and we have a lot of languages, multilingual queries coming over. Over the period of time, we also see that these kind of multilingual queries have changed their behavior So earlier we used to have a lot of Turkish queries coming, Arabic queries coming in Deutschland, but over the period of time, it's more of Russian queries, more of English query, as and when the customers are evolving. Last, but a very important one, assortment issue. What if we don't even sell those products, or they're out of stock, or maybe they're not live right now? So we thought, okay, sure, we have vector search. Can it help us in a lot of things? Sure. 4 out of 5 can be easily solved, at least in our theory that it could be solved via vector search. But one issue still remains: assortment. What happens with assortment? So we thought, okay, is it a temporary thing? Is it just because it's out of stock, or we don't sell it, so maybe we need an alternative? So we analyzed further and divided into head queries and long tail queries, and analyze how frequently they are temporary versus permanent assortment issues. And we saw almost like 20% of the head queries could be solved over 7 days of rolling. And it could be because of business rules being added or the product again being in stock. But this problem stays longer for the long tail queries. So we definitely need more, just than more semantics, we need alternative products as well. So we started with our first iteration on analyzing. Let's not go much deeper and use existing LLM products and existing LLM models and see how these public models work for us. So we did our first iteration. But before we get into that, a very important thing, how do we evaluate? And so any model is really important, how well it performs offline. I think Doug had a presentation day before, and he presented a really nice pyramid, which states 95% of the effort should go into offline evaluation and 5% in model building. And that's what we started with the offline evaluation. So we said, okay, now we have a lot of data. We have this problem understanding. What would be a good evaluation? Would just a text evaluation mean it's a good result? Well, not clearly, because we still had issues with these examples. Let's say Spül machine, 45 centimeter Einbau. Sure, there is the match of 45 centimeters here, but is this the important token of the query? Or what happens if it's a semantic thing? So Spül machine matches with Geschirrspüler, but if you just look at text matching, it doesn't match really well. Then the next idea was to use implicit feedback. So we do have, over a period of time, collected a lot of implicit feedback where we had queries and results. What do we use it for? The problem with that is we don't have implicit feedback for a lot of products. Sure, we have head queries, which is contributing a lot of our traffic, but that also means that only a limited amount of products would have these good amount of implicit feedback. And also what happens when the product that we suggest via our semantic search is still relevant, but it's still not popular? Would we say it's a bad result? No. So we went on for further analysis, and we got into this idea of category-based result mapping. So what we are doing here is we are trying to analyze the category of a query, a search query, especially from the head queries, because we have enough traffic for it. So we analyze, okay, this is the query category, and now we're trying to match it with the product category. So let's say if we are looking for iPhone, we should be okay if we are showing Samsung, because it's still a smartphone, and we're still working with fallback. So we're not going to be really strict with our first iteration. And so we decided to go in the first iteration. I'm not sure if this is really clear, but with the root categories, which is like a website category, and we're just sticking to the roots here, because even if we are, let's say, looking for notebooks, it should be fine if we are getting a monitor or a PC in a result. And this is where we got into our first evaluation iteration. We further divided into granular matrices so that we can analyze how it's working well for semantic queries, multilingual queries, long queries, short queries, and so on and so forth. Then I'll hand it over to Johannes.
Yeah, and on the training side, of course, the most important question was first which model to choose. So, and actually, yeah, when we were searching in Hugging Face, for example, for models, we discovered the same, like I'm discovering for 10 years now already. Everything is nice if you search for English language, but for German, not that well. Yeah. But we found a couple of multilingual models, and what we were particularly interested in to test different model sizes and yeah, test different models regarding their pre-training. So we were, of course, particularly searching for models that were tailored to retail search, but actually also we were not that successful with this. Still, we found a couple of models. I mean, many of them might be familiar to you. And then we created a first data set for triplet training, different sizes. First, we had a 70,000 triplets, and then 550K, and then 750K. But actually, the amount of triplets did not make a big difference. It was like always, anchor positive, negative. So we had a query and a product that we assumed to be relevant for this based on sales and click and metrics and so on in the context of the query. And yeah, we started with a very naive approach of selecting negatives, and this was first random and then a little bit more sophisticated. Actually, we excluded substrings, so or actually we included them. Yeah, and what we discovered is, I don't know how well this can be viewed. Actually, yeah, we quickly identified, okay, those triplets, they are simply by far too easy. If you simply select random products as negatives, it's too easy for the model to compare that the positive is closer to it's closer to the query than a random product. And yeah, the same happened when we were running the training and then estimating its quality. It increased a little bit, but then it got stuck in about 50% model quality with the category-based evaluation. So, but it was quite obvious actually that we had a couple of issues. They became quite clear during this first iteration. The first was that actually the triplets were simply too easy. So the negative selection was too unsophisticated, was too easy that, for example, a washing machine is very different to an iPhone. So that was, even for the public models, easy to identify. So the fine tuning did not improve the model quality that much. Second, as you can see, this is an exemplary description of a notebook. Actually, and this is randomly selected, so you will find many of such product descriptions in the MediaMarkt web shop. This is typical for consumer electronics, and what you can see already, actually, this is very different to what the public models are trained on. They are mostly trained on Wikipedia data and so on. And I mean, we have already been talking about the series number. In here, you can see what the tokenizer does with this. So it splits it up to single characters. And if we consider that actually all those tokens are assigned to a vector and then they are pooled by some kind of algorithm to a single vector, actually, then it's quite clear that the more terms you have there and the more tokens you have there, the fuzzier it gets. So for us, it was quite clear we need to focus much more on product descriptions. We need to focus much more on smartness of negative selection. And furthermore, we also decided to train our own model because the vocabulary of the public models were simply, we considered as not suitable. And this was also the beginning of the second iteration where we started custom model training and especially put much more focus on producing product descriptions.
So as it said, any model is as good as the data is. So we started working on our data, and like you see here, a search query being Apple MacBook M1. And now we see a lot bigger product description. So usually we did an analysis of about 90% of our queries being up to 4 tokens longer, and an average of 10 tokens in the product description. So it contains a lot of redundant information, a lot of noise. And also, since we have a structured data, a lot of structured features, over like 100 of features per product, are being stored. And so an important question, what would these product description mean? And can we just include only the important information out of this product information? So our first iteration was that what if we just map these common terms between queries and products? Sure, it worked well, but it also led to a lot of loss of information. So most of the important tokens of the product description, we lost it. Also, it might not always map to user query. So for example, a user might look for Apple MacBook M1, while the product description can say Apple MacBook M series. So it's not always a very direct mapping. So what we thought of using entity recognition. So we thought we have a lot of user queries. How about we analyze their behavior, and how about we analyze what kind of queries they have and what important features are they looking for? And obviously it varies per different categories of the product. So a smartphone query could vary in the features or important features versus a notebook query could vary differently. So what we did was we analyzed user behavior by taking all their queries and analyzing what all important features of a product are they looking for. So here we find different patterns. So for example, notebooks had a lot more of processor model information in that, versus a smartphone could have color information. A notebook might not be important with the color. Also, then we shortlisted these important categories and tried to build our own product description instead of this large product description. So we also tried to figure out that, okay, because these are different kind of products and the queries from user behavior also varies, we also analyzed that this is not only on the important features, but how longer the query is. So for a washing machine, they might just say a brand and model, but for a phone or maybe drone or maybe notebook, they are more specific in what they want. So they're looking for more features. So that's why we have dynamic features. So this is what we did in the first iteration. We took up all the important features from the queries and tried to build our own product description in a dynamic fashion. I can give you an example here. With the notebooks, we found out all these important candidate features, and this is the actual product description for now. You can see Acer, Big Bebek, and then here's the search query, laptop 17-inch, Zoll, Windows 11, this being the product description that we have as of now on the website. And this is what we are creating, the more concrete, more important features one, to vectorize, and hence reducing the noise here.
Yeah, in the meanwhile, we also became a little bit smarter regarding training. And I think one paper particularly inspired us, and this was published by Amazon. Actually, they have a 4-stage training. They first train a very large model with purely with product descriptions and with masked language modeling. Then they have another masked language modeling step where they combine, this is the second one, where they combine queries and products to single texts. And afterwards, they apply a triplet training. This is the third step here. And finally, they reduce the large model to a smaller model in order to be more faster and so on. So this inspired us, and actually the things we had set up already and that we had planned, they were quite similar, but of course ours were less sophisticated because we weren't that far with implementation and so on. So we simply picked out the steps in between and applied first a masked language modeling basic training with a model from scratch, and then a triplet training as already described before. Yeah, what do I mean? So the training from scratch, actually masked language modeling, I guess most of you will know, but simply we produced query product tuples, as you can see. So for example, iPad, tablets, Apple iPad, and so on. And then we mask tokens in between. And yeah, and these tokens get predicted. So, and yeah, and as you can see already, this kind of training is it's not that difficult. I experienced that small batch sizes work much better than, or much more stable than large batch sizes in this case. But we also compared several different parameters regarding predefined vocabulary size and so on. But actually, they admit they did not make that much of a difference. And particularly, what needs to be considered is a very small predefined vocabulary set works better for masking, but worse for later steps. So, the core acknowledgement here is that actually you should never only watch at the metrics of the masking itself, but the full chain of trainings need to be considered particularly, because actually even if it works better for masking, it might not work better for the later steps. Yeah, and for negatives, I first completely failed because I implemented some kind of approach that you build of all training. I think it was 1 million tuples, an in-memory index of vectors and scores, and then I take the first or the closest the closest false positive over the entire index. And what came out is that if you do something like this, it's by far too much because you overwhelm the model. So this is quite nice. So if you overwhelm people, it's finally the same. So they will simply get annoyed by this. And finally for models, this is the same. So it's simply, I think it over adapts. And so if you challenge it with too difficult negatives, or the negatives are simply too difficult to acknowledge, and particularly if you combine this with small batch sizes, then the model quality heavily decreases and it will never recover from that again. So you can simply stop those trainings. So, but then we discovered an approach that worked quite very well. So, and it's the creation of how you create so-called semi-hard and hard negatives. So, and it works in a way that you have a batch, and within that batch, you create embeddings for all queries and products in the batch, and then you assign labels on whether it's would be a hard negative or a semi-hard negative. And a semi-hard negative is if the negative is far away from the query than the positive, but still close. So this is semi-hard, and the hard negative is if the negative is closer to the query than the positive. So this is a bit more challenging then, because actually there's something definitely wrong. So the semi-negative is already somehow correct. So it should still continue to modify the parameters in this way. And the hard negative is something that is wrong. And what is in line with what we discovered is as well, you need to be sensitive to a model regarding triplet training, and you need to start with easy ones, and then you can start with the harder ones. So this is something you can see on the left bottom. Actually, this is the hard negatives percentage during the training. I started with a very soft approach, and then I became a little bit harder. Yeah. And finally, this worked out very well. Actually, it gave us a plus in the quality metrics of 0.3. This is 30%. So the training, the model then worked 80% as expected for shorthead and for tail. Even though there are still queries that are unsuitable, actually the primary purpose of what we're doing is for zero results. And during manual, or in the context of manual assessments, we discovered that it works quite well for really a lot of zero results. So even though it's not perfect as of now, we definitely think this is the time now to expose this to customers, because we are convinced that we have some kind of minimum valuable product already. And this is also the third iteration. Now this is the striving for the MVP.
So in the previous iteration, we show how we are building product description, but it still comes with a lot of shortcomings where we have marketplace as well as retail products. So obviously we're not having only the retail catalog being maintained by the product catalog managers, but we also have user data coming in, which also leads to the fact that we don't have the product catalog being well maintained. Some of the information might be missing, the descriptions could be too long. Features disambiguation is another issue that we figured out. So for example, we have iPhone 14 Pro, and 14 could be mentioned by a user in different field. It could be like a height, which is weird, but that's how user maintain the catalog. Then we also needed to have a lot of handcrafted rule to extract these features. Obviously, there was not one-to-one mapping between the products and queries. So there are different ways product are being described versus how user use them in queries. So we need to have all these handcrafted and regex, unlimited, yeah. And then of course, we have a lot of redundant features. So with each product, we have hundreds of features in our structured data. Could be package information, storage information, capacity, which are redundant, but could still match to the query, which we don't want. So another solution was that we leverage our business partners and use their information and knowledge. So they also maintain for some of the greatest, most popular categories, this important catalog, and they, over the period of time, have analyzed and realized what all important features are. So it's just the business knowledge. And we are trying to integrate the business knowledge along with what we have identified from our algorithms. So here you can see the example for smartphones. You have business features that are important. We have recognized some of the user behavior features. And here you see the dual SIM is missing. And this is where we kind of give it a boost and create our new descriptions here, which is much more intrusive.
Yeah, I think so we have actually in the current iteration, we have two streams. The first is making it improving the product description, which is something like, I think this will never end. And the other is making it technically ready. And I won't talk too much about it, but I think it's worth mentioning that we're talking so much about databases in the context of vector search, but I would say always first think about libraries and not about databases, because it heavily depends on the size of data, whether you need a database at all. So actually the most easiest approach is if an indexing or if replacing an index simply becomes a deployment and everything is put into a single service with a library instead of a database. So there in many cases, so no suggester needs a database. No, if you and the good thing is also that for vector search, it's very predictable. The size of the data is very predictable because you have a static size of vectors and so on. So and if you create a container or if you create an image that contains the model, the index, and fully runs in memory, then you can simply run it on a serverless engine. And this is quite important actually, because normally these teams are full of data scientists or full of data people who are not aware of how to run a service in production, which is a very difficult thing on a retailer. So I think you can, in general, things can be done way easier if it's simply everything put to a single component, and there is not always a need for a database, just to be clear here. I think we're in a quite good situation as of now. We're confident we have a minimum valuable product, so we will run the A/B test soon. We have done all main implementations. But what I also realized is that training is much more about building software than I expected it to be. So there's a lot of stuff is publicly available, but it still needs to be integrated in the infrastructure. It still needs to be into something that is into a common solution. Still different training options need to be set up. You need CI/CD for models and so on. But actually, we have done all these things. So yeah, we can now put much more emphasis on even more experimenting with spellings, addressing multi-language. So the stuff we were talking at the beginning, in the meanwhile, we have focused a little bit more on the semantic stuff in order to get an MVP done. And yeah, we have also ideas to integrate OpenAI or Gen AI models into the public or commercially usable Gen AI models into it in order to get more stuff done, more features covered. Thanks.
Any questions?
Lot for the great talk. Initially, you said that the pooling is one problem that you had with open models or with the publicly available models, and that is one problem for your product IDs. And the pooling is still in your trained model is still a problem because you still have a lot of very specific concepts that are in the title that somehow get very specific vectors and they're pooled, and all this specific knowledge that you train somehow is lost in the pooling. But token level matching, which allows you to do this on somehow exactly utilizes this information that you have in each single token instead of someone pulling this information away.
We have been thinking about this, but this is rather a next step then. So I think the most important things that gave us the most boost on model quality were not necessarily the training from scratch, to be honest, because it was rather the product descriptions and the sophisticated triplet training. So because with this, even the public models work a lot better. So I mean, the ones with the base are still a little bit better, but I think we would now with the triplet training and with the good triplet training and the valid product description without too much noise, we would even have an MVP with a public model. So I'm as of now, I'm not sure how important this step was to be honest. We will see in the future maybe if we add more features or the like, maybe then it's more beneficial. But as of now, I would say that it was maybe a good decision because we understood more, but it was rather about understanding and not that much about quality, at least as of now.
Hi, thank you for your talk. It was quite interesting. I'm just curious, in terms of latency, it was mentioned that it's low latency, and my question is, how low is this? Is it like tens of milliseconds or it's hundreds of milliseconds?
No, it's less. So if you simply run it in the same container, you can even run it on CPU, and the latencies are still very low. So
okay. And how well it scales? Like if you have hundreds of requests per second?
Yeah, well, the good thing is if you simply put it into one image, then you can scale it horizontally because you can start so many images. Doesn't matter, and you only have one single component for load tests. So you don't have things like could be the latency between database and service or whatever. You have your service, you have your code there, you have all your business logic there, and without any additional components. So you can simply run this on a serverless engine, and then you don't need to worry too much about these things.
Okay, so without further optimization, so for LLM to get, for example, the vector for the query, it takes like tens of milliseconds, right? Something like this. So yeah.
I wouldn't even say tens, but yeah, a very short time.
Thank you.
I mean, on GPU and distributed is even faster, but this is not needed. So this also works on CPU.
Thanks for the talk. You motivated the model for result searches. Are you combining it with the classical search, and how? Or are you just using it as a fallback for zero results?
You want to answer?
No, so for now, we're just going to be displaying those results as zero result or at page where we don't have enough results. So the request is going to go in parallel, but we're going to display it only if it's a zero result or a less number of results.
Thanks.
We did have a slide, but we skip it for that. So sorry.
But maybe let me add one more thing to that. The classical search will never be removed because actually 60% of the use cases or even 70% of the retail search use cases are very simple. And they are in a matter like, in a way like, give me an overview for something. I want to see all your iPhones. I want to go through it and I want to sort it by price. I want to do these things. I want to explore what you have. So I mean, the person that René quoted initially, actually, I feel with those people who still work with keyword search, yeah, this person is definitely not working in the context of retail.
So maybe a last one.
So thank you for your talk. So about the vector-based search, the in-memory index. So are you talking about like exact or approximate vector-based search? So like nearest neighbor, I guess. And what kind of algorithm have you been using?
You mean which library or?
No, the algorithm itself. So like if you go back to the slide where you say you build an in-memory index for vectors. If you just do like exact, so you literally just scan all the vectors and measure the distance with the query, or something different.
Sure. Yeah. So we are using HNSW library from Python.
Any reason you didn't consider you mentioned Solar, right?
Yeah, but you know, different teams, this will happen. We will use the stuff you built. Definitely, yeah. So, you know, but I mean, Doug initially talked about this, right? So it's sometimes you have a very complex search solution. So I think, to be honest, if you have new ideas, one of the first things is, of course, whether they work. But before you even start exploring, you should have a rough idea how this could fit into the landscape. I think that's also the difficult part because this is where most data scientists struggle with. Yeah. So, but if you don't, I mean, you cannot expect people to implement your ideas. This is not going to work because you will miss too many things. If you want to push something, you will most of the times fail, I guess. Or you have an idea how this could be integrated, and we will, yeah, because this is as of now it's too difficult. It looks like what Doug presented there. So, but as of now, it's a fallback. We cannot break anything if we release it for zero results and so on and so forth. So we have a plan. That's fine. So,
thank you.
But yes, and I can write you if we are using Solar for that.
Okay. So we are a bit behind the schedule. So maybe ask your questions in person later. Yeah. Thank you very much.